I'm going to explain trig identities from section 5.4. We had been going over that in class, and we had been given some basic trig identities. I'll be giving you a sheet with those on it. But example 3 on page 260 had given us cos x over 1 minus sine x equals 1 plus sine x over cos x. So we had already proven that it was true for 30 degrees, but they also, in part C, we're going to skip B, in part C it says use an algebraic approach to prove the identity is true in general. In other words, we're going to use the trig identities we have already learned, and we are going to prove one side equals the other side. Okay, so we're going to prove that. Now, there's different ways that you can go about this. Maybe I'll do it a couple of times and show you a couple of different ways. Okay, so the way that I would do it is not the way they do it in the textbook. So I'm going to do it my way, and then I'm going to explain their way. When we prove identities, there's not one way to do it. As long as you use your trig identities and you use them properly, there may be several ways to prove one identity is equal to the other. Now, what I had said in class is, generally speaking, try and work with one side versus the other. And I said that unless you have fractions. In this case, we have fractions. And whenever I have one fraction and an equal sign and another fraction, I tend to like to get rid of the fraction by cross multiplying. But what I mean by that is take the top of this and multiply it with the bottom on this one. So cos times cos would be cos squared x. On this side, I would cross multiply, and I would have 1 minus sine x times 1 plus sine x. Now, there's not a whole lot to do on the cos squared x side. That's pretty simple already. But on this side over here, we have 1 minus sine x times 1 plus sine x. We could do FOIL with that. Now, it's really a difference of squares because I have a minus and a plus, and that's the only difference. So really all I have to do is firsts 1 times 1 and lasts negative sine squared x, because the middle piece would end up being plus sine x minus sine x, which would be 0. So you don't really need to do that. So now I have something that reads cos squared x is equal to 1 minus sine squared x. So the two sides are not equal yet, okay? However, remember, and I'm just going to write it over here. Remember in class we said one trig identity is sine squared x plus cos squared x equals 1. And what I said was you can rearrange that in any way that would be beneficial to you. So if I move this sine squared x over to this side, I have something that says, I don't know why I did that. I have something that says cos squared x is equal to 1 minus sine squared x. So if that's true, if cos squared x is equal to 1 minus sine squared x, and I have 1 minus sine squared x here, I can replace that with a cos squared x, which is what I had on this side. So now I have the two sides equaling one another, and I have proven that identity. Now that's how I would do it. It is not the only way. So let me talk about how they did it in the textbook. Okay. So in the textbook, they chose to go about this differently than I would choose to go about it. So let me explain their way and see if that one makes any more sense to you than the way I did it. So again, we start off with cos x over 1 minus sine x equals 1 plus sine x over cos x. And so what they chose to do was they chose to work with just the left side of the equation. So what they're going to do is they're just going to work on the left side and try and turn it into what's on the right side. And so what they said was, what they're going to do, and remember, you can do anything you want. If you do something to the top, you've got to do it to the bottom. If you do something to the bottom, you've got to do it to the top. So they decided they were going to multiply the bottom by the conjugate, by exactly what's on the bottom, just with a different sign. Because what that does is that makes 1 minus sine squared x, because it's a difference of squares. So I do 1 times 1, positive sign times negative sign, and I get 1 minus sine squared. But whatever I do to the bottom, I have to do to the top. So I'm not going to write it all out. I'm just going to say I would also have to multiply the top by 1 plus sine x, because if I multiply the bottom by 1 plus sine x, I have to multiply the top by 1 minus sine x. Now, again, look at that bottom. It's 1 minus sine squared x. And just like when I did it my way, I said, remember, sine squared x plus cos squared x equals 1. That's one of those identities we talked about. And I said you can rearrange it. So if I move my sine squared x over here, I'm going to have cos squared x equals 1 minus sine squared x. So if I have a 1 minus sine squared x, I can replace that with cos squared x. On the top, I still have cos x times 1 plus sine x. Now, I have a cos on the top and a cos squared on the bottom. This cos will cancel one of these coses, and I end up with 1 plus sine x over cos x, which is exactly what's on this side. I have just proven it. All right, we're going to look at another one. Example number 4. Example number 4 on page 262 is very similar to this last one. The instructions are similar. The question's not necessarily similar, but the structure of the question is similar. So in this one, they give us tan x minus 1 squared equals secant squared x minus 2 tan x. Well, this is just lovely. All right, so first off, they want us to prove that this is true when x is pi over 3. Now, personally, again, I don't like radians, so pi over 3 would be 180 divided by 3, so that would be 60 degrees. So they want us to prove that is true for 60 degrees. Now, I know my 60-degree triangle. I'm just going to put it over here. My 60-degree triangle, you should know, is 1, 2, and root 3. That is my 60-degree triangle. So this is actually tan of 60 degrees minus 1 squared is equal to secant squared of 60 degrees minus 2 times tan of 60 degrees. Now, I wouldn't even bother to write that line out. I'm just doing that so that you can see what I'm doing. So tan of 60 degrees. Tan is opposite over adjacent, which would be root 3 minus 1. So I just replace the tan with the root 3, and then I have the minus 1, and that is squared, equals secant of 60 squared. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So that means secant is hypotenuse over adjacent. It is 2, but it is squared minus 2 times tan of 60. And tan, again, is opposite over adjacent, which is root 3. So we're going to work on both sides. Root 3 minus 1 squared is root 3 minus 1 times root 3 minus 1. If I do FOIL with that, root 3 times root 3, that's 3. Root 3 times negative 1 is negative root 3. Negative 1 times root 3 is negative root 3. And negative 1 times negative 1 is positive 1. So 3 plus 1 is 4. And negative root 3 and negative root 3 is negative 2 root 3. On the other side, 2 squared is 4 minus 2 root 3. Oh, look, the two sides are equal. They're the same. So I've proven that what they put at the top is true for a 60-degree triangle, but then they say they want you to prove it in general. In other words, use your identities. Use algebra and your identities to prove it. Okay, so again, there's more than one way to do these, generally speaking. So let's look at, you're going to have to pick a side to look at. And again, there's lots of ways to do this. So tan x minus 1 squared would be tan x minus 1 and tan x minus 1. If I do FOIL with that, that is tan squared x. If I do tan times negative 1, that is negative tan x. And negative 1 times tan is negative tan x. And negative 1 times negative 1 is positive 1. Now, that would be tan squared x minus 2 tan x plus 1. Now, back on page 259 in example 1, they give you an identity that says 1 plus tan squared x is equal to secant squared x. That's an identity. That's just something, if you see a 1 plus tan squared x, you can replace that with the secant squared x because that's a known identity. So I have a tan squared x and a plus 1. I can replace this with secant squared x, and then I have minus 2 tan x, which, by the way, is what that side is. So I have turned the left side into what the right side says. And that's what they want you to do. Okay. So example number 5, that was 4. Example number 5 says, this one looks very long. Cos squared, now they put a theta, I put an x, it doesn't matter. Cos squared x over 1 plus 2 sine x minus 3 sine squared x, that's very long, equals 1 plus sine x over 1 plus 3 sine x. I'm trying to look and see. Again, we can do this. I don't like, they do for radians. I don't want to do that. So I'm going to change that example a little bit. And I'm going to change that to be prove that's true if x is, let's say x is 30 degrees. So we're going to prove this for a 30-degree triangle. And a 30-degree triangle is 1, 2, and root 3. Okay? So if I'm going to prove this for a 30-degree triangle, we're going to do cos squared of 30 degrees. I'm not going to bother to write that out. So cos of 30 degrees is root 3 over 2, adjacent over hypotenuse, squared. Now, I'm going to write it horizontally, divided by 1 plus 2 times sine of 30, and sine of 30 is a half, minus 3, and sine of 30 is a half, squared. 3 sine squared. Okay. So I have root 3 over 2 squared. That is 3 over 4. Divided by 2 times a half is 1, minus 3 times 1/4. 1 squared is 1, 2 squared is 4. So this is 3 over 4 divided by 1 plus 1 is 2. So this is 2 minus 3 over 4. So 2 minus 3 over 4 is 1 1/4, and 1 1/4 would be 5 over 4. So I think that's 5 over 4. So I have 3 over 4 divided by 5 over 4. So keep, switch, flip. 3 over 4 times 4 over 5. My 4's would cancel. And I end up with 3 over 5. So hopefully I end up with the same thing over on this side. On the top, we have 1 plus sine of 30. And sine of 30 is a half, divided by, and again, I'm just writing this out horizontally instead of vertically, 1 plus 3 times sine of 30, and sine of 30 is a half. So I have 1 plus a half, which is 1 1/2, or 3 over 2, divided by 1 plus, that would be 3 over 2. That would be 1 plus 3 over 2, and 1 plus 3 over 2 would be 5 over 2. So keep, switch, flip, keep, switch, flip. My 2's would cancel, and I'd end up with 3 over 5. So both sides give me 3 over 5. So I have proven that this is true for 30 degrees, but then they want you to prove it generally. In other words, using your trig identities. So again, there's different ways to do this. How would I go about this? I don't know yet, honestly. I kind of do this on the fly. So if I were looking at this, some of the things I said were try and get things in terms of sine and cos. Now, one thing I would look at is I have sines here, I have sines here, I have sines here, and I have sines here. And it's like this cos is the odd thing out. So I think I'm going to try and change that in some way. Now, how am I going to change sine into cos? The only thing that I can think of where I could somehow do that is that I have this identity sine squared x plus cos squared x equals 1. And if I bring my sine squared over here, I have cos squared x equals 1 minus sine squared. And if that's true, then on the top, I can replace cos squared with 1 minus sine squared. Now on the bottom, I have 1 plus 2 sine x minus 3 sine squared x. That looks like a trinomial to me. So let me forget, I find it hard to factor something when there's sines and coses in the way. So let me just write that as 1 plus 2x minus 3x squared. So I just took the signs out of there so that I don't have to look at those. If I were trying to factor that, 1 times 1 would make 1, and then 3x and x would make 3x squared. Now, if I had plus here and a minus here, let's see if that works. And again, I'm just going to check it. 1 times 1 is 1 square is 1. 1 times negative x is negative x. 3x times 1 is plus 3x. Negative x plus 3x is plus 2x. So this is it factored. So 1 plus 3 sine x. I'm just going to put the signs back in now. And 1 minus sine x. All right. I might be getting closer. What I notice is over here on the bottom, I have 1 plus 3 sine x. Over here, I have that on the bottom, but I have this extra piece. Now, 1 minus sine squared, that is actually this part right here. 1 minus sine squared x is actually factorable. That's a difference of squares. I can make that 1 plus sine x times 1 minus sine x. That will give me 1 minus sine squared x. On the bottom, I still have 1 plus 3 sine x and 1 minus sine x. So now look, I have a 1 minus sine x on the top and 1 on the bottom. Those will cancel. And what do I have left? I have 1 plus sine x over 1 plus 3 sine x, which is exactly what I have here on my right side. So I have proven one side equals the other side using trig identities. Again, is that the only way? Maybe not, but it's what I figured out. All right. Example number 6. It just says we're only doing part A of example 6, and it gives you 1 over 1 plus cos x plus 1 over 1 minus cos x, and it says it wants you to simplify. It's what it says it wants you to do. Okay. There's no equal sign, so you're not proving one side is equal to another side. So you're not proving that. What you are going to try and do is get this to look a whole lot simpler than it looks now. How am I going to do that? Not sure yet. So I'm going to look at this and I'm going to say I'm adding fractions. If I'm adding fractions, I need a common denominator. And a common denominator would be 1 plus cos x and 1 minus cos x. Both of those things would have to be in the denominator. I can't get rid of the denominator. There's a fly in here. I can't get rid of the denominator because there's no equal sign. It's not an equation, so I can't cancel them out because there's no other side to deal with. So I can't get rid of it. What I can do is get this common denominator. So up here with this piece, if I want to turn 1 plus cos x into this lovely denominator, I would need to multiply by a 1 minus cos x. But whatever I do to the bottom, I have to do to the top. So Here I have 1 times 1 minus cos x, which is 1 minus cos x on the top. Plus, here, to get the common denominator, I would have to multiply by 1 plus cos x. That would give me that common denominator. That means I have to multiply the top by 1 plus cos x. When I do that, 1 times 1 is 1, and 1 times cos x is plus cos x. So, on the top, I have 1 plus 1, that's 2, and I have negative cos x plus cos x. Those actually cancel out. On the bottom, I have a difference of squares here. I have 1 plus cos x times 1 minus cos x, which is 1 minus cos squared x. All right, go back again to that trig identity that says sine squared x plus cos squared x equals 1. Rearrange it. This time, move your cos over. Sine squared x equals 1 minus cos squared x. So if I have a 1 minus cos squared x, I can replace that with a sine squared. Well, right here, I have a 1 minus cos squared x. So I really have 2 over sine squared x. Another way to think of that is 2 times 1 over sine squared x. You have another identity that says 1 over sine is the same as cosecant x. So 1 over sine squared, so we have this 2 here, and 1 over sine squared could be secant squared, because I have a 1 over sine squared, and 1 over sine is cosecant, so 1 over sine squared is secant squared. This is much, much simpler than what we started with, so that is as far as we're going to go with it, because I can't get it any simpler than that. So I would be done right here. All right, that is it. I will be assigning some questions for you to try. We will likely be going over, not likely, we will be going over a lot of this in class together. All right, so we're going to be doing lots and lots more practice with these. So if you're finding these difficult, that's perfectly normal. And we're going to be doing a lot more of these together. All right, bye.